Swayam Prabha. Digital India. Educated India.
Let us now discuss the implementation of the BEQ and BGT instructions. So recall that BEQ is branch if equal. So equal means that the equal flags.e bit is set. Means that the last comparison resulted in an equality, and flags.gt is used for the BGT instruction. Means that the last comparison resulted in one number, the first operand, being greater than the second operand. So let's look at BEQ first. Oops, sorry, this should be Q. Alright, so first thing that we do is that we test the flags register. So we invoke the MBQ micro instruction to test flags.e. So recall that flags.e is also a micro register that is exposed on the shared bus. So we compare flags.e with 1. If there is an equality, then we jump to the dot branch label. Otherwise, so otherwise pretty much, if there's no equality, this instruction is as good as a no op. So we then again proceed to the next instruction. So we jump to mb.begin, which means, sorry, this should again be here. mb.begin, which means that we move to the beginning of the preamble. So if, let's say, we are branching, then what we need to do is that we have already computed the branch target. So recall that the branch target was computed in the decode stage. So the branch target was saved in a separate micro register. For non-branch instructions, it contains junk. But for branch instructions, it contains a valid branch target. So we move the branch target to the PC register, and then again we jump to the next instruction, the beginning of the preamble. But this time when the preamble executes, it will see an updated value of the PC, which is the target of the branch, not old PC plus 4. So it will start execution from that point. The BGT instruction is implemented in exactly the same way. It is just that instead of comparing flags.e with 1, we compare flags.gt with 1. If there is equality, we move to the dot branch label. Otherwise, we move to the preamble. And then we move the branch target to the PC, and we start executing the preamble for the next instruction at the branch target once again. Let us now take a look at the call instruction. So the call instruction is very similar to the branch instruction. It's just that a little bit of more work needs to be done. So what we need to do is that we need to save the value of the PC after the call instruction, the next PC, into the return address register. So if you would recall in the preamble, so in fact in the third statement of the preamble, we had actually incremented the PC by 4. So we had set the current PC equal to the old PC plus 4. So that we had already done. So what is there in the current PC is actually the old PC plus 4. So we don't have to increment it once again. We can directly write it to the return address register. So what we do is that we transfer the contents to the reg data micro register. This is what is supposed to be written to the register file. Then we transfer 15 to reg source. So why 15? Because 15 is the ID of the return address register, is the ID of array. And simultaneously, we send the write command on the shared bus. So basically what we are doing is that we are writing the value of PC, the value in the PC register, which is the current PC plus 4, which is essentially the address of the next instruction, to the register file. And which register? The register file, register 15 array. Once we have done that, we can jump to the branch target. So we load the branch target in the PC, which is equivalent to a jump, and we move to the beginning of the preamble. such that we can execute the next instruction. Let's next look at the ret instruction, which is nice and simple. So what this does is that we read the return address register number 15 and save its contents in the program counter, the PC. So alright, so what we do is that we load 15 into reg source with the mmove I instruction, mmove immediate, and we simultaneously send the read command on the bus. So we read the register. The data will be available in the micro register reg val, which will essentially contain the return address. This we move to the PC. So once we have done that, we can again jump to the beginning of the preamble and execute the instruction at the return address. Let us now consider an example. So let us change the call instruction to store the return address on the stack instead of in the array return address register. So we'll just show the microcode. The preamble will not be shown because it is common to all the instructions. So a stack based call instruction is like this, that the first thing that we need to do is that we need to read the value of the current stack pointer. Then we need to decrement the stack pointer and store the return address there, and we need to return. So let's read the stack pointer first. So the first thing that we need to do is that we move the ID of the stack register, the stack pointer register 14, into the micro register reg source, and simultaneously we issue a read command. So we are basically reading the value of the stack pointer from the SP register. Once we have done that, the value of the stack pointer will be in the reg val register, which is the output of the read instruction, of the read micro instruction. So now what we do is that we will decrement the value of reg val by -4, which essentially means that we are creating some space on the stack. So if let's say this is the last element on the stack, we are decrementing the stack pointer by 4 bytes, which is the size of an integer in a 32-bit system. And we are creating some new empty space where something can be stored. So we are essentially decrementing the stack pointer here. So we read it first, then we use the madd instruction to add -4 to it. So we decrement the stack pointer. And once we decrement the stack pointer, this becomes the new value of the stack pointer. So what we simultaneously do is that since we need to store something over here, we send this to the MAR memory address register, MAR micro register. So we send it there using a simple mmove call. So we send the updated value of the stack pointer, which is the old SP -4, to the MAR micro register using an mmove instruction. So this will be required when we will store the return address. Now let's come back. Now that the stack pointer has been updated, it needs to be written back to the register file, right? So what we will do is that we will write it back. So since we'll write it back, which register are we writing it back? We are writing it back to whatever is stored in reg source. Since 14, the ID of the SP register has been stored in reg source, and we have subsequently not changed reg source, so the value 14 will remain, the stack pointer will remain. Reg val has been updated with this madd instruction, where we have essentially computed the new stack pointer, which is old SP -4. So this value will be written back. So the way we will do it is that we will write it to reg data, which contains the data that needs to be written, and simultaneously we'll issue the write command. So this will update the value of the stack pointer inside the register file, and the new stack pointer will be the old stack pointer -4. So the register file will thus contain the updated value. Once that is done, so we need to write the return address to the to the new location on the stack that we have just created, and the return address will be there in the PC register. The reason being that if you would recall the third or the fourth instruction in the preamble, was that we are incrementing the PC by 4, right? So PC is equal to PC plus 4. We already had this part in the preamble. So maybe let me quickly go back to the preamble and show you. Yeah, so this is where we had m add PC4. So, yeah, back. All right. So we have already incremented this by 4. So this contains the return address. So we move this to the MDR micro register, and simultaneously we issue the store command on the bus. So this ensures that we store it to this location on the stack. So let's see how. So the MAR register, which contains the address, already contains the location of the new stack pointer. This has been done here. So the address is correct. And now we transfer the data. What is the data? Well, the data is the value of the return address, which is stored in the current PC register. This is transferred to the MDR micro register, and simultaneously we issue a store command. So as a result, in a new stack location that has been created, the return address is stored over there. Now that we are done, we finish the execution and we jump to the beginning of the preamble by calling the micro instruction mb.begin. So this instruction is, this example is indicative, it is representative of a whole host of optimizations and complex instructions that we can add with the microprogramming mechanism. And we can also change the behavior of current instructions. For example, let's say we take the call instruction. We change this behavior to actually write the return address on the stack, right, instead of in the array register. And similarly, we'll have to modify the ret instruction as well, but it's possible to do all of that. And it's possible to do all of that fairly easily, in fact. So the important point that we are making here is by exposing details of the internals of the processor, we can implement new instructions, make existing instructions work differently, and this can help us add a lot of additional extremely sophisticated mechanisms to our processors. Alright, now that we have seen most of microprogramming, let's quickly take a look at the microcontrol unit, or the unit that runs these micro instructions. So this is the shared bus. We have up till now been looking at it as one set of parallel copper wires, right? That's the only way that we have been looking at this. We have not been looking at it, very differently. But now we will sort of create a more complicated structure, and we'll see how it works. So the way that we design the shared bus is like this, that we actually have two buses, a write bus. So a write bus is a set of copper wires where all the registers, the micro registers that can write to it are connected. So all the decode registers like IR and RS1, RS2, RD, all of those decode registers, the PC register, they're all connected to the write bus. Similarly, all the register file, ALU and MEM unit micro registers are also connected to the write bus. So all of them dump their values to the write bus. Of course, all of them are not activated at the same time. So we have separate activation signals for one. So only one of these registers is activated. So an activated state means that it can write its value to the write bus, and the rest of them are quiet. So we will need separate control signals for them. I have not shown that. The details are in the book. Subsequently, what we do, so this is one of the inputs from the write bus which can go to this multiplexer. We call this multiplexer the transfer multiplexer in the book, mainly because it transfers data from a writer to a reader. That's all. We don't use any other sophisticated terminology. In addition, we have a microcontrol unit. So the microcontrol unit parses the immediate field, just in case there is a micro immediate that we are using, like an madd or something, or mmovi. So in this case, the micro immediate is added to whatever register value is being sent on the write bus. And the added value is the second input. Like in an madd instruction, the result of the addition of the micro immediate with the micro register value, this will be sent to as the second input of the transfer multiplexer. So let me give an example. Let's assume that we have a micro instruction of prototype M at PC and 4. So essentially PC will dump its value in the right bus and the micro immediate is 4. So both of them will get added and that will be the result of the addition of the second input. The immediate itself can be an input to this transfer multiplexer, and this will be in the case of M move I, which we have actually seen. We have seen M where did yeah, this is where we saw, right? M move I reg source 14. So what M move I is doing is, so let's see. So in this case, we take the micro register and we move a constant to it. And this micro immediate can be one of the values which is being, one of the values which is being transferred from a writer to a reader. So that's the reason it is also one of the inputs to the transfer multiplexer, which is controlled by a set of control signals, which we shall discuss later. In addition, for finding out whether the micro instruction, whether the branch instruction MBEQ, whether there is an equality or not between the immediate and let's say the value in a register, we also have an equality circuit here, which compares the value that compares the value of the immediate and also the value of one of the registers. So it compares both, and then what it does is that it generates an equality signal. If there is an equality, then the is M branch signal is true, otherwise it is false. After this, so these are all the macro registers that are writing to the write bus. On the read bus, the read bus will essentially transfer values to the micro register. So the read bus will transfer values to the PC, and that so in a sense the PC can be updated. And how will it get updated? By any one of these mechanisms that can be used to update the PC. So that will read its new value from the read bus, and also micro registers of the type MAR, MDR, right, regval, and so on. So all the other micro registers associated with the register file, ALU, and mem unit, they can be updated via values coming from the read bus. So they will read it from the read bus and update themselves. So that's the way that we'll build our circuit. All right. So there are two kind of ways. There are two types of microprogramming. One is called vertical microprogramming, which has some advantages, and the other is horizontal microprogramming. So let's consider a micro instruction and how it's encoded. So this is one particular way of encoding a micro instruction. So in this case, we use 3 bits for the type of the micro instruction. So we have 8 micro instructions, we need 3 bits. 5 bits for the source registers. Actually, if you count, we have a lot of source registers, right? So basically 5 bits for the source register, 5 bits for the destination register, 12 bits for the micro immediate, 10 bits for the branch target in the microcode memory, right? Because we're assuming the memory is not very large, and also so we are also assuming that the memory is organized in this fashion, that in each entry there is one micro instruction. So we don't have to go from one entry to the other. We don't have to add 4. We just have to add 1, which means the next entry. So 10 bits means a table with 1024 entries. So 1024 micro instructions. That's the size of all the micro instructions. That's the size of the microcode sequences of all the instructions that we support. Then we can have a 10-bit value for the args field. Out of this, 3 bits can be for the unit ID. So which unit are the arguments meant for? And are they meant for the register file or the memory unit or the ALU? And 7 bits for the type of operation that we want to perform. So this part is slightly over-designed, but nevertheless, over-designing is also useful if you want to extend the design. So the total number of bits are 10 plus 10, 20, plus 12, 22, 27, 30, I'm sorry, 20, plus 12 is 32, 37, 42, and 45. So this is a 45-bit instruction that we can create, a 45-bit encoding that we can create for every micro instruction. So what is essentially required, to process this is actually a processor which will have a fetch stage for the micro instruction. So these are there in the book. Then it will have a decode stage where essentially this 45 bits is decoded, and subsequently an execute stage where the actual micro instruction is executed. So at least we need a 3-stage processor to process this. So I'm not discussing this in detail because they are there in the book. And also it'll be a kind of repetition because we have already looked at a lot of processing in the previous lecture, so I don't want to talk about the same things over and over again. Another way that we can do this is horizontal microprogramming, where we actually get rid of the decode state. So so we assume that, so what does decoding give us? Decoding gives us the values of all the control signals, right? Well, in principle, we can take all the control signals and because for every instruction we can compute its control signals, and we can encode the control signals themselves. For example, let me consider an instruction of the type m add pcn4. So then that would maybe generate a long list of control signals, some zeros and some ones and so on. So one is that we separately encode madd, separately encode the PC register, separately encode 4. All of that is good. But another way can be that of course, we need to encode the value of 4 as an immediate, but for the rest, we can just have a list of control signals which will control which part of the circuit are active and the values of the read bus and write bus, right? The control signals for the transfer multiplexer and so on. So we don't need a decoding stage at all. So this is called horizontal microprogramming, where the control signals will directly be part of the instructions encoding. So in this case, we'll have 10 bits for the branch target. Fine, fair enough. We'll have 12 bits for the micro immediate, 10 bits for the argument, same format as this, 3 bits for unit ID, 7 bits for operation code. In addition, instead of having these other fields like type of instruction, source, these 3 fields, right? We'll get rid of this. Instead, we will have 33 bits, a bit vector that encodes all the control signals. Where does 33 come from? Well, readers need to go to the book, so a breakup is given. But the long and short of it is, the summary of this is that we are getting rid of the decode stage completely, because the decoded information will be part of the instructions encoding. So we don't need a separate decode stage. So this will essentially be a 2-stage processor where you have fetch and execute. So the advantage is we are getting rid of the decode stage, so our logic will be simpler and the processing will be faster. That's the advantage of horizontal microprogramming. The disadvantage of horizontal microprogramming is that we'll have a longer instruction. It will take one instruction, will require more bits to store, so it will require 65 bits as compared to 45 bits for vertical microprogramming. So number one will require more size, which, well, in some cases is okay, in some cases it's not okay. But the other bigger thing is that we'll have to expose all the details, including control signals of the hardware, to firmware, right? So that, if this is hardware and this is firmware where, all our microcode is there. Previously, we are just disclosing the names of the micro registers and so on. So for vertical microprogramming, that was fine. But for horizontal microprogramming, we'll have to disclose all the control signals, right? And this might be too much, number one, from a security point of view. Number two, we have absolutely no flexibility in changing the design. Even if we change the design a little bit, these control signals will change, and as a result, the firmware will become useless. As compared to that, if we use vertical microprogramming and we still keep the register names and IDs the same, for example, we still have PC and IR and RS1 and RS2 and so on, But if we make some internal changes and the control signals change, it will not affect us because we still have a decode stage, and the decode stage inside the microprocessor, not the microprocessor, the microcode unit of the processor, will generate the control signals differently. So we still have some, freedom and flexibility. In this case, the amount of freedom and flexibility that we have is pretty much non-existent. The reason being that we will not be able to make any change, even if there is a minuscule change in the hardware and the control signals change. So there is clearly a trade-off of flexibility here. If I consider horizontal microprogramming and flexible and vertical microprogramming, if I see the size of the instruction, size of inst, right? So in this case, well, this is bad and this is good. If I consider maybe, speed and complexity, then, this is good and this is bad. If I consider flexibility of, changing the control signals or other, simple details of the hardware, horizontal has no flexibility at all, whereas vertical microprogramming still gives you some amount of flexibility. So there is clearly a trade-off between both the approaches. It's not the case that one approach is strictly better than the other. So these have to be kept in mind. Alright, so here is a quick description of the of the microcode execution engine of a vertically microprogrammed processor. So this is very simple, so we are not discussing this in great detail. So we have a micro PC which goes to the microprogram memory, and it basically is incremented, which sequentially scans it unless there is a jump. It reads each micro instruction which is sent to the decode unit, which generates the control signals that go to the execute unit. The execute unit uses the control signals to control the data path as well as the shared bus, notably the transfer multiplexer. And that's how the execution is performed. In addition, the data path sends the opcode to a specialized unit called switch, which tells the microcode unit which location in the microprogram memory to jump to. That is one input of this multiplexer. In addition, we can have a micro branch, so that we can have a branch target. So this can go here, right? So this location can definitely go here. And then the default will be that we will add 1 to the current micro PC, which is the next micro PC, not 4 but 1, because it's entry wise, not byte wise. So the micro mux will choose one of these three targets and choose the next micro PC. This is as such, an extremely simple processor, which basically has a fetch unit over here, which has a decode unit over here and an execution unit over here. And the execute unit basically lets the circuit run with the control signals that have been generated by the decode unit in the previous cycle. So that's pretty much all. That is there to this. I just have one clarification to make. So there's a little bit of confusion regarding the terms, but there should not be. So this branch target is actually a micro branch target. So maybe I'll update this in another version of the slides. The slides that are there on my website. So this should actually be the micro branch target. It is not the simple RISC branch target. Rather, it's a branch target in the microprogram memory. And this will essentially come into being because of the MB and the MBEQ instructions. So they will, make the microcode jump from one place to the other. So it is that branch target. It's not the simple RISC branch target. That needs to be kept in mind. Alright, so this is the processor design for horizontal microprogramming, which is equally simple, but it's slightly simpler. So most of the circuit remains the same. We still have a micro PC over here, which supplies the value to the microprogram memory. And since all the control signals are already embedded inside the micro instruction itself, we just have a fetch stage and an execute stage. The control signals are sent to the data path where they control the movement of data and also the transfer multiplexer. In addition, we have, actually two multiplexers here. So this multiplexer essentially gets the micro branch target, right? Should be the micro branch target. And because, just so that we don't confuse it with the branch target micro register that we have, which is actually for simple risk. So this is the micro branch target and also the default next micro program. So we choose one of them, and that is one. And in addition, what we do is so basically, the way that we choose. So I'll just tell you why we have two multiplexers here. So we have one M1. So essentially, if the instruction is a branch and if the branch is successful, if it's taken, then we will choose one of these. Otherwise, if this instruction is not a branch and it's not relevant, then essentially we move the both the branch targets and the default next microprogram PC, right, to the micro marks. So yeah, this part could have been designed differently, but the main spirit of these two multiplexers is that we'll use the is M branch signal mainly for comparing with an immediate, which is basically MBEQ. With the MBEQ micro instruction, we compare the value of a register with an immediate. So this will only take care of that. Other than that, we'll use a micro branch target, let's say for an MB kind of instruction. So that we'll directly use in the micro mux. And this will serve as the default, right? Which is the default next microprogram counter. In addition, we'll send the opcode to the switch unit, which will generate the address in the microprogram memory that we need to jump to for a given simple risk instruction. So we need to choose among these four inputs. Of course, in theory, the M1 mux could have been removed and we could have just had the micro branch target and the default value, right? Possible could have been done. We just thought it'll make the control circuitry slightly more complicated. This was slightly simpler to design and visualize. That's the reason this design was chosen. And there is no other reason. There's no other reason why this cannot be removed. It's just the logic has to be changed a little bit, but it's still fine. And once we choose a next PC, this can be fed to the microprogram counter. The next micro PC, that is, we can send it to the microprogram counter. Alright, so this brings us to an end of the chapter on microprogramming. And we will then look at making processors and processor design much more efficient. So we'll discuss a technique called pipelining in the next chapter, which is chapter 9.